Okay, so we are doing the second parent graph. You guys ready? Ready for this one? Okay, e to the x. Okay, e is Euler. It's spelled like this. Everyone wants to pronounce it Euler. It's Euler. 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 Not Euler. Don't say it with a southern accent. Euler. Okay. And don't say Euler. E is Euler's number. Euler's number. Euler's number E is kind of like the idea of pi. You know, it's like a symbol that has a special number to it. There are two buttons on your calculator that do it. An E all by itself is above the division sign. So, and it's in blue, so we're going to hit second division sign. That's just the E, 2.718. That's what it stands for. E is almost always used to an exponent, almost always. So the button you will typically use on your calculator for it is above the LN button, which is right next to the 4. The LN button is right next to the 4. The E to the X button is right above that in blue. So second LN is how we will typically use the E, because E almost always has an exponent. It's very rarely by itself. If you want to get E without an exponent, you can either use the option that's above the division symbol, or you can do E to the 1 using the one that's above the LN. Okay? So Euler's number, 2.718. Okay? Not Euler. I won't judge you, but if you go into college and take a math class and you say Euler there, they will judge you because they're pretentious there. Okay. Euler's number 2.718 is the E number. So if it's just E, 2.718. Now, E to any other exponent would be different. Kind of like if you had pi to the 5th, that's different than just 3.14. I did second ln, and then I just typed in a 1. So if you do second ln, that's E. E is usually raised to an exponent. Almost always. Yeah. Okay, so that's E to the x. E is approximately 2.718. That's Euler's number. Okay, so we're going to do the same thing that we did with the parent graph y equals b to the x. We just know that this one is special. It's a specific base number that happens to not be a whole number. It happens to be a decimal, and it's very common. In fact, when you get into a level such as calculus, you never use a base number that's a whole number anymore. Well, not never, but mostly never. You use e to the x like 99% of the time. They just like ditch 2 to the x, they ditch 3 to the x, they ditch 4 to the x, they ditch 10 to the x. They don't care about any of those. They always use e to the x. And in fact, it's easier, and that's why they do it, because e to the x is the easy one. Okay? So e to the x, we're going to do our best to not be intimidated by it, because e is just a number kind of like pi is. Okay? So here we're going to say, just like the regular parent graphs for b to the x, we're going to say the horizontal asymptote is 0. It still has the special points where you plug in 0, you get 1. You plug in 1, you get the base. We just know that the base for these problems is Euler's number, which is 2.718. So it's not scary, it's just a decimal. That's it, 2.718. And then the information for this base, which would be E. Yeah, you can write an E there. Yeah, it just works out the same as the other parent function did. Yeah. So the transformations work the same as the other parent function, so I'm not going to make you write it twice, but we know that the base is the growth rate. We know that if a is negative, it reflects it over the x-axis. We know that if A is a number that's bigger than 1, it stretches it vertically. If A is a number that is less than 1, it compresses it vertically. We know that in the exponent, we're going to consider that to be like the inside of the function, and so that's left and right, but it's kind of the opposite of the signs. And we know the number on the end is up and down. So I'm not going to write it again because we already wrote it. We've written it a lot of times. Okay. So did we do example 1? Yes. Okay. And we talked about domain and range and that stuff. We did example 2. We did example 3. Okay. We need to do the x and y intercept. Okay. So let's go ahead and do example 4. So I'm just going to do second plus 712 and get my calculator back to normal. I don't know who used these last in class. I can't remember. So I'm going to type in negative, and then I have an exponent here, so I'm going to do second ln. So I can do the e to the exponent. And then I got x plus 5, and then plus 1. And make sure when you type this 1 in that the x plus 5 is in the exponent spot, but the plus 1 is not. Everyone got that typed? Yep. Okay. And what should the horizontal asymptote be? 1, right? Because that's the number on the end. So this is the same as last unit, right? The same as last unit. So it's a horizontal asymptote, the number on the end. What's another name for horizontal asymptote? Anyone remember? It's the k value. And they call it horizontal asymptote, but what's another name for the type of asymptote it can be called? Starts with an E. I told you. Nope.
It's like the word
E. And I said, what's another name for what that asymptote can be called instead of horizontal asymptote? They call it end behavior asymptote. They call it end behavior asymptote. Remember, because the horizontal asymptote gave us the numbers for our end behavior last unit. And so this number contributes to our end behavior, right? Not as much as it did last unit, but it's still going to contribute. Okay, so let's go ahead and hit the graph button. Okay, so our x-intercept, it's over here on this side of the graph. So for me, whenever I see that, I'm going to use -10 and 0 for my left bound and right bound because I'm lazy. So second trace, number 2, -10, enter, 0, enter. The guess is stupid, so I'm going past that. Ooh, look at that, it's a whole number. That's nice. -5.
Oh, is the x-intercept also the opposite of x plus 5? Or that's how I got it.
That was a nice coincidence. Not always, no. So second trace, number 2. Okay. How do we find the y-intercept? Second trace, number 1, plug in, 0. Okay.
Wait, so to find the exact x value, so don't you have to like move a little bit or something?
Nope.
Left bound, blank, left bound, right bound.
That's really because every time I put in left bound and right bound, it will still make me move.
Oh, on the one go on
If you so you can
you have to move it.
now if you don't type in a number, it'll make you move. But you can just type in a number and then you don't have to move. So when it says left bound and right bound, you can do that with your cursor, or you can do that by typing numbers in. So we did it by typing in numbers. We told it to look between -10 and 0. And then we didn't have to move. The other option is you can do second trace number 2, and you can actually scroll and say, there's my left bound, there's my right bound, and the calculator can look for it that way. So you can either do it by moving, or you can do it by typing numbers in and having it look between those two numbers you typed. Yeah. Yes.
Yesterday on the test, there was one that was asking for the intercept, and I was doing it on the calculator, and there was a line that went like this, and then a line that went like this, and that was the one I was going to find, was this one. And every time I was typing in left bound, this, right bound, this, it kept going to that graph. graph up there and giving an error because it didn't cross to the x-axis. So I had to like move it closer to, like I had to like press the button closer to this one and then do the left bound, right bound.
Yeah.
So I don't know. It was weird. But I'm pretty sure I got it to work.
Mm-hmm. Sorry. Okay, so we want to do second trace, number 1, plug in 0. So we got 0, negative 147.413. And then this is our second unit in a row where we don't have maxes or mins because we don't have mountains or valleys again. So no maxes, no mins. Okay. Let's turn to the next page. Did we do end behavior? Yeah. We did? Okay. We did not do 5 and 6? No? Okay. All right, so let's find all the things for 5 and 6. So first, we can find the transformations. What are the transformations? Okay, reflect over x. Okay. Down 1. Left 2. Does it have a vertical stretch of 3? Yes or no?
No.
What's the parent graph?
Yes.
Y equals what's the parent graph? If you can figure out what the parent graph is, you'll know if the 3 is a stretch or not. It's what? You are close. Y equals... The parent graphs are either y equals b to the x or y equals e to the x. Those are the parent graphs. Okay, so what's the b? Can the negative... Well, the negative is either reflection or it's part of the b. Which is it?
It's the b, and the negative is the reflective over x.
Okay, so if the negative is part of the base, then it's not a transformation. Okay, the negative is a transformation, so it's not part of the base. Okay, the negative is not part of the base. Okay, so what is the base? The base is 3. So the parent graph is 3 to the x. So is the 3 a stretch? No, because it's the base. Do you see how it gets to be one or the other? It doesn't get to be both. It is one or the other. So the negative is in front of the 3. It's not the base. Now, if the negative was the base, and this would not happen, by the way. This would not happen. But if the negative was part of the base, it would be written like this. Do you guys see the difference? This is how the negative also gets the exponent. But negatives they are not bases. They are transformations, they are not bases. Does that make sense? Okay. Now, if you were to have a stretch, it would look like example 6. Do you see the big difference between example 6 and example 5? So it's got an extra number in the front. That's what it looks like to have a stretch. But just having a 3 there, no, that's the base. We got to have some sort of base to have an exponential equation. Because you can't say your parent function is just like y equals an exponent of x just chilling, hanging out in the air with no base there. You got to have some sort of base for the exponent to be there. Does that make sense? Okay. So the 3 cannot be a stretch because it doesn't make sense for an exponent to be there without a base attached to it. We got to have some sort of base. Okay? All right. Perfect. All right, so we got the transformations down. We need to find our special information. So we need the horizontal asymptote. We need 0, 1, 1b, So we need to do all of our transformations on that. So horizontal asymptote starts at y equals 0. And then let's go ahead and move those points. So what should we do first? Reflect over x. So that's not going to change the horizontal asymptote. It's still y equals 0. And you can actually, if you want to, we already know that the horizontal asymptote is -1 because it's just on the end. Do you guys like writing that in from the start, or do you like doing it with the transformations? Doing it from the start? Okay. Okay. Okay, so first transformation is reflect over x. Let's write in our base for this problem so that we can do these transformations properly. So the base of this problem we already know is 3.
So when it's e of x, the base is just going to be
The base is e, which is 2.718. Yeah. Yeah. Okay. So we'll reflect over x, so it's not 0, 1 anymore. It's going to be 0, -1. And it's not 1, 3, it's 1, -3. Okay? And then we have to go down 1, so how do we do that? Subtract 1 from the y. So -2, -4. And then how do we go left 2? Subtract 2 from x, so -2, -1. Okay, so I'm going to draw the asymptote.
Wait.
And then when I start these, I always start with the point that's closest to the asymptote and then draw away. What? So we had -2, -2, and -1, -4. We need the domain and the range. What's the domain? Left forever, right forever. Okay. What's the range? Negative infinity to -1. It goes forever. It doesn't stop.
Because the x value.
It goes right forever. It just is super slow. Yeah, and if you graph it on a calculator, it looks like it stops, but it doesn't. Yeah.
So will it ever pass?
Yep. Oh yeah. It very, very slowly. If we graphed it on Desmos, we'd probably have an easier time seeing it, but yeah. All right, so we have domain and range. There's a very strange bug on my desk. All right, what else do we have? Increasing and decreasing. Okay, so here's our stick figure. Our stick figure's walking which direction? Downhill. Okay, here's a negative infinity. Here's a positive infinity. Oh, yeah, left to right. Negative infinity to positive infinity. So for increasing, I'm going to put none. For decreasing, I'm going to put negative infinity to positive infinity. I need my x and y intercept. Okay, negative 11, and we got that just from plugging in 0. I'm gonna plug it in real fast to make sure that everybody knows how we got that. So here's our equation. And we're doing second trace and plugging in second trace, plugging in 0. Ooh, negative 10. So the y-intercept is negative 10. X-intercept? Nope. The asymptote keeps it from ever going there. Okay. Max and min?
You should put that on a test between like max and min and then have some random points and then one answer be
That
valid.
would get. So would. So it would never cross -1.
It would never cross negative 1. Okay, so max and min are none. Is the graph continuous?
Yes.
Yes. Okay, and then end behavior.
These graphs always continue.
Yes.
And is the end behavior still at like the other ones where you just put the
You can't put the horizontal asymptote for both. Yeah. So when we look at the left arrow, what do we notice? Goes to the horizontal asymptote. So the left arrow goes to negative 1, which is the k value. The right arrow does not go to the horizontal asymptote, though. Where does the right arrow go? You're close. It's not the k value, and it's not positive infinity. That's the x. It's going down forever. Negative infinity. So for this, so for this unit, it's a little bit more difficult than last unit was. Last unit was nice because it was always the horizontal asymptote on both sides. This unit, it's going to be the horizontal asymptote on one side. Yeah. All right. Next one. Transformations are.
now this is a stretch.
Vertical stretch of 2.
So your base is 4, right?
Base is 4.
Right 2,
Right 2.
down 1.
Down 1.
I mean,
Up 4.
I'm looking at
Up 4, it was a typo. It's fine. Yeah. All right, so we've got the horizontal asymptote is y equals 4. And then we got 0, 1, 1, the base, and then what's the base? 4. Okay. How do we vertically stretch 2? Times 2. Which coordinate? Y.
is it X or
Y. Because you want to vertically stretch. So that's an up and down. So we're going to do 0, and then 1 times 2 is 2. 1, 4 times 2 is 8. Okay. Next, we want to go right 2. Yep, add 2 to the x coordinate. Then we want to go up 4. 6, 12. Why did I make one that you can't draw? Miss Rice. So 2, 6, 3, 8, 9, 10, 11, 12. Okay. So domain range. What's the domain and range? Okay, domain, all real numbers. 4 to infinity. Does the 4 have a bracket or a parenthesis? Can you show me where the 4 is, where it equals 4 exactly? Yes. For these particular graphs, yes. Now, does the graph touches 4 or does not touch 4? Does not touch 4, so it gets a parenthesis. Okay. Okay. Increasing, decreasing. We look at our stick figure. Our stick figure is walking uphill. Okay, so we've got negative infinity to infinity. Okay. X-intercept. There's no x-intercept. The y is 2 times 4 to the x minus.
Yes, it is a comparison because one is the product of another. It is.
Perfect.
Yes, it is. Repetition and consistency.
beside each other and saying they're the same thing because they basically all. She
No.
can tell you it's something that
But a lead pencil is not the product of a regular pencil. Repetition creates consistency. A regular pencil does not create a lead pencil. But it didn't create it. No, it's not. Okay, we're in an argument because I'm right and they're incorrect. They're saying that they're saying that repetition and consistency are the same thing. And I'm saying no. I'm saying, and they're agreeing with me that consistency is the product of repetition, but then they're trying to say that the product of something is the same thing. And I said, okay, well, you are the product of a sperm and egg, so if you put a sperm and egg on the table, and then you put you beside it, are you guys the same thing? And they're like, no, but that doesn't make sense. Yes, it does. Because it's the same. No, I don't care because I'm right.
All right, the only way we can settle this is if you guys fight in the parking lot. Let's go.
Okay, but that was whose argument is it?
All right.
No, fight on the stairs where everybody else fights.
Is that where we fight? Is the stairs?
Last year.
All right. So we have domain range, increasing, decreasing, x and y. Now we got to do max and min. None. Oops.
It's not there either. Or, I mean, it is. I'm glitching out now.
Max, min, none, none. Continuous, yes. End behavior. We're going to look at the left arrow. We're going to look at the right arrow. What do you guys see as you look at the left arrow? Y is 4. Okay. What do you see as you look at the right arrow? It goes up. Okay. Okay. Perfect. All right. You guys excited for some assignments?
Assignment, does it plural?
No. Well, I mean, there's the assignment, the practice assignment, and the notes. So, you know. All right. Of course, I didn't get to staple